Today I've been experimenting with this Gravitech kit. It's a stepper motor and a stepper motor driver, as you can see back here. And over here we've got the Raspberry Pi and the breadboard, and that's pretty much it. Let's look in detail on each one of these. This is the stepper motor, 5 wires, got a plug on this end which is keyed. You plug it into that board, not much to it. I put a flag on here so we can see it rotating. It's got flats on both sides of the shaft and mounting and so forth. This is the driver board. It's got 4 LEDs over here on the left side and the plug for the stepper motor. Back here is the power supply. It says 5 to 12 volts. I'm only running on the 5 volts from the Pi. And then here are 4 wires from the Pi, and I've run those through some resistors just for fun. And you can see it says input 1, 2, 3, 4 down this side there. And this appears to be an enable and jumper on the chip here on the board, and then our driver chip, and that's pretty much it. So let's keep following these wires back and see where they go. This orange, blue, green, and yellow wire, they come over here, go down to our breadboard, and I just simply put some 330 ohm resistors across between the stepper driver and the Pi. Just, I don't know, safety measure, makes me feel better. I'm not sure it's necessary. Okay, and on this side, same wires. You can see yellow goes to yellow, green to green, blue to blue, orange to orange, and then they come back here to the Pi. And here are our power supply. So this is the 5 volt from the Pi, and this is the ground from the Pi. And then just the pins, 7, 11, 13, and 15 if I recall. We'll take a closer look at that, but that's it. So there's the wiring. A little bit more complex, but not too terrible. Before we get into the nitty-gritty of the software, let's take a look and see what the software does for us on this system. We'll get it cranked up. We should be able to see our little tape flag here turning, and the LED lights will blink. However, when the motor is running at high speed, they blink so fast they look like they're on solid. Okay, let's take a look and do a demo. And so behind the wires, it's asking us back here how many revolutions we want. Let's just do 1 revolution. And then the next thing is whether we want to go counterclockwise or clockwise. And I will just do the defaults. And here we go. Again, the lights look like they're on solid, but they're actually blinking very fast, and the flag went around exactly 1 time. Okay, let's run it again with some different parameters. This time let's run it at, say, half a turn, maybe a quarter of a turn, 0.25. And we'll do the counterclockwise, just for fun, -1. And the speed, we'll just go to, well, let's do a slow speed. We'll do a 0.01, a little bit slower than the default. And now you can see the lights flashing. And you can see that's turning, but quite slowly. And there's our quarter of a turn and done. Okay, so now let's go see the software behind what makes this happen. This is our software that makes it all happen, that makes that stepping motor run. And we'll start off up here at the comments. I'm using the Gravitech ROMT0647 stepper motor kit. It's a very nice little kit, not very expensive. It comes with a 28 VYJ motor, which is 12 volts. I'm only running it at 5. It's 2-phase. The gear ratio of 1 to 64, and each angle that it turns is 5.625 degrees. That's the minimum it will turn. 4,096 cycles running through here will create 1 full revolution. And the chip on the board, in case you're interested, is the ULN 2003 chip. It's a very common chip. We import the time function so that we can use sleep, and we import GPIO library so that we can use the pin functions, the pin numbering. I'm going to use the board numbering scheme, and my pins are going to be 7, 11, 13, and 15. Those are all output pins, so I output each one of those in sequence so that I can turn the stepping motor. Here I set those pins. I just use a loop because it's easier than writing out all of that code, each one of those steps individually, and then I set each pin to false. I just turn it off to make sure that the stepper motor starts up in the off condition. Here are some variables I need to keep track of stuff. The step sequence number, here's the step sequence down here. I need to know where I am in this table. And the rotation speed, this is a delay that allows me to slow down the stepping motor. Here's the rotation. It's 4,096 steps equals 1 revolution, as we said before. And the rotate direction, it's either 1 for clockwise or -1 for counterclockwise. This little bit is a table that actually is what causes the stepping motor to turn, so it's very important. The table comes from the specification sheet of the manufacturer. You can see over here, maybe you can't, but it says like orange is on, step 1 orange is on, the second step orange and yellow are on, and then on the third step only yellow is on, and then the fourth step yellow and pink are on, and it goes that way across the table. So I have just coded that table into here. You can see here's orange on, and then orange and yellow is on, and then yellow is on, and it goes on through here. And what this represents is each one of these little bits represents one of the wires that's coming out of our Pi. We're using 7, 11, 13, and 15. So this is 7, 11, 13, and 15, and this represents whether that particular pin is turned on or off. And you can see this wave, see the wave of ones traveling through there? And that's what nudges that stepping motor around, is we give it a little bump, a little magnetic bump by turning on a pin, and another one, another one, another one, and we keep giving it a little nudge, and that's what pushes it around in a circle. One pass through here is 1/4096th of a revolution. So one pass through here is about 1/4000th of a turn of the shaft. And yeah, and if we execute it going from here to here, it's going clockwise, and if we execute it backwards, going from step 8 to step 1, it's counterclockwise. This orange, yellow, pink, and blue, those represent the wires that are going into the motor. There's actually 5 wires, but we're only concerned with these 4. And so that's the explanation of this little table right here. Again, very important. And this is the heart of the whole program, is executing through this table multiple times. This is where I ask the user for the inputs, and I check to make sure that the inputs are within a range, to do some error checking, in other words. So the first one is I'm just asking for the number of revolutions that the user wants. And of course you could call this as a function. You could rewrite this as a function and use it, in your robot, and use this whole thing as a subroutine to move the wheels or arms or whatever you're doing. But the first thing is the number of revolutions of the shaft, and if you use 0.00041 as the input, it turns it roughly 1/4000th of a turn of a revolution. So it will accept decimals, and it will accept up to 100 or 1,000 revolutions, whatever you want to do. The second 2 variables are the rotation direction and the rotation speed. So I ask for the direction. 1 is clockwise, -1 is counterclockwise, and the speed is anywhere between 1 and 0.001. It's a delay. So the bigger the number, the more it slows down. Anything more than 1, and the motor is turning so slowly you can barely see it. It's like a minute hand on a clock. So I limited the upper end. Down here I just do some checking. I want to make sure that this rotate F, the rotate float, is within a range. I grab that, I multiply it times the 4,096 to convert it into degrees rotation, if you will. And if it's out of range, I default to 4096. Then onto the rotation direction, which is right there. Rotation direction, integer of rotate dir. And yeah, just grab that, and again I do some error checking to make sure it's either 1 or -1, and if it's not, I default to 1. Rotation speed, I just take float of rotation speed, which is input right here. And if it's out of range, then I force it to the fastest. I found that if I try to use a delay any less than this, sometimes the motor skips. In fact, it usually skips, and it falls short in the total rotation it's supposed to make. And then there's a debug statement I forgot to take out, but I just print this data so I know what it is. This is the main routine of the program. This is where all the action happens. And it's going to execute through this table. So we talked earlier about this table. This bit of code right here is going to walk through this table time and time again. So we start out and we want to know how many times we're going to rotate. So how many times through this table are we going to go? And again, we have to go through this table 4,096 times to get one rotation. So we're going to look at each one of these groupings. Each one of these groupings represents the 4 wires that we have that we're using. So pin 7, pin 11, pin 13, pin 15. And we're going to determine whether pin 7, 11, 13, or 15 should be turned on. If there's a 1 in this table, the pin needs to be turned on. If there's a 0, the pin needs to be turned off. So that's why you have this little loop right here that goes from 0 to 4. It's going to walk through each one of these values of each one of these groups. And when it's done with that, it's going to go to the next one, and we're going to loop through and we're going to walk through each one of these bits. And again, we have to execute all of these bits 4,096 times to get one revolution. So here's what we're doing. We look at the first group, and we're going to look at, in this case it'll be pin number 1. We'll start out with pin number 1, pin 7, and we're going to look at that, and it says, okay, that should be 1, and yes, that's right, it's 1, so we're going to turn GPIO output of pin 1, or pin 7 rather, to true. Okay, so we go through that, and we'll come back up here, and now we're on to the second bit, and it comes to here, it says, is it equal to pin 1, is it equal to 1? And the answer is no, and so it false. So we want to turn that pin off. So pin 11 will be turned off, pin 13 will be turned off, pin 15 will be turned off in this little loop for the first group. Now, we move on. We need to move on to the next set, and that's what this little bit of code does. This keeps track of where we are in the groups. So we need to sequence. We need to go from this group to this group. So we do that. We add the value, we increment by 1. We move to the next group. And so let's say we're going clockwise. We'll just do the first part of this. If the step sequence number is greater than or equal to 8, well, no, it's not. We're still in group 2. Then we're going to leave it alone. We're just going to increment and move on. But let's say that we're down here to the bottom and we're at 8 and it's okay, greater than or equal to 8. We need to go back up here. This is like a circular queue. So we're going to execute this group to get one revolution 4,096 times. So we reach here, we've got to go back up again. We've got to go back up again. We've got to go back up again, just like this. And this is the bit of code that's keeping track of which group we're in and whether we need to reset and jump back to the top of the group. If you're going counterclockwise, it's just the opposite. You're going this way until you reach 0, and then you got to jump back to 8 and then keep going this way. The last thing is this time to sleep. This is not perfect. It varies. The speed will vary with the changes in program. For example, if you put a print statement somewhere in here, you're going to find out your stepping motor slows way, way, way down. So the sleep is not an exact time, but it allows you to tune the speed of the stepping motor pretty well. Okay, so once we execute the number of rotations that we're supposed to do, we've gone through this table, rotate number of times. We fall through, we do the GPIO cleanup, we reset our output pins, and we print done so we know we're done. And you could easily turn this into a function for your robot or whatever you're using it for, their wheels, their arms, whatever. But that's pretty much it for today. I hope you found it useful and interesting in your Raspberry Pi and stepper motor experiments.